Now what we're going to be doing with these inequalities is we're going to be solving them similarly to what we did when we solved equations. We still want to isolate the bars, but when you have what's called a greater than statement, okay, greater than or greater than equal to, when you get to the separate step in isolate, separate, solve, this time when you separate them, you're not just going to separate it to positive, negative, you're going to separate it to ax plus b greater than c, so like literally the exact same thing, and ax plus b, flip the sign, flip the positivity. So we switched the inequality sign to the other one when we made the other side negative. Okay, so separate step still has separate, and you still change one to positive and one to negative, but you also flip that symbol. Do you see that? Okay, that's going to give us the two things that we're going to be able to solve. So you're switching the inequality and you're switching the sign. That's super important right there for the separate step. And the same thing's going to happen for either of the two less than statements. When you separate them, so we isolate, we separate like we did before, this is going to be ax plus b less than c, so literally exactly what we started with. And then ax plus b greater than negative c. So again, we're flipping both the symbol from less than to greater than and the sign of c to negative. So you have two things to change when we separate. But other than that, we're still going to use the ISS steps. What did the I stand for? Isolate. We wanted to isolate the absolute value bars so that they're all the way by themselves. That step, 100% the same. What did the first S stand for? Separate. And that's when we're going to separate it into the positive and negative versions, but we also flip that symbol whenever we separate it. So let's remind ourselves that. We're going to separate it into positive C and negative C, but also remember to flip the symbol. Okay. What did the second S stand for? We had isolate, separate, solve. Yeah, and then we're just going to solve for x. And this time we're not going to get x equal a number and x equal a number. We're going to get two new inequality statements. Something like this and something like this, depending on what symbol you started with. So just like before, we had at the end x equal number, x equal number. Same sort of thing, however, they are now inequalities since we are solving an inequality. There should be no equal signs in your answers. If you did that, you accidentally just changed the whole problem. We're not doing that. We're doing inequalities. Okay? Since these are inequalities, we are not just finding single number solutions, we're finding entire inequality solutions, which means we're finding and or inequality statements. So for and statements at the very end, this is going to happen when you are using the symbol less than and less than equal to. When you have those two signs, when you start, the final answer is called an and statement, and you're going to color between the two solutions. And what I mean by that is, when we solve this inequality, last time we would have found two solutions, and we put those, you remember putting those little dots on the number line? This time, we're not only putting the little dots on the number line, we're also going to color in between them on the number line. So it's a set of numbers on this number line instead of just two dots. So what this means is, if we were solving this first one, it's isolated, right? Okay, so I can separate it. We're going to separate it into x less than 2 and x, flip the sign, flip the sign. So we flip the symbol, we change the sign. This is my and statements. I would put the word and in between these two things. X less than 2 and x greater than negative 2. But what that looks like on a number line is I have the symbols for negative 2 and 2, and all of these numbers in between them on this number line are actually what my solutions are. I can pluck out any number in that number line and it would work. Now I have a little bonus question for you right now. I went ahead and did it, but why, perhaps, maybe we can remember, why did I make these open circles?
Because that's not like the answer. Because it's not equal to.
Bingo. That's fabulous. It's not equal to. These symbols don't have the little line underneath them. Do y'all see that? These symbols? No line underneath it. So that means I'm working with this inequality back when we did set notation, and that inequality has an open circle. So I would put an open circle around those numbers on my number line. If my symbol had the line underneath it, literally all that would change is you'd fill in the dot. That's it. Okay? On the other hand, an or statement is how you would write your final answer for something that's greater and greater than or equal to. This time, you're not coloring between, you're going to color on the outside of these numbers. Helpful, or outside, both start with O. That's how we can remember that. So what I would do is, again, if I were solving this inequality, absolute value of x greater than 2, we would isolate, check. We would separate into the exact same thing I see and flip the symbol, flip the sign. But instead of putting the word and in between those, I'm literally going to put the word or. So when you write your answers, you can't say and this and that. For this type of symbol, you would say or. But what that does for my number line is I still have -2 and 2, but this time I'm going on the outside of them and coloring in both outsides, not between them, on the outside. We're saying x has to be greater than 2 or x has to be less than -2. This is where x is greater than 2. This is where x is less than -2. And it's the word or in between them, not the word and. Again, I chose to use open circles because these are not equal to. When that has a line underneath it, you'd make these filled in circles. Okay, so the isolate, separate, solve stuff, same thing we've been doing since forever when I started teaching you absolute value inequality or equations. However, because it's an inequality, at the very end you have to go, is this and or is this or? And here's one way I've always, as a student, that I learned this and it has stuck in my brain for forever. So what we're going to do to help you remember if it's and or, you're going to misspell these words. Less than, right? This is not how you spell less than, but watch this. Less than. If I just add a D right there, what kind of statement is less than? An and statement. If you misspell the word greater, this is not how you spell it, I know that. If you misspell the word greater, what kind of statement is it? Or. So the word itself will help you remember if it's and or. Less than, and statement between. Greater, outside, it's an or statement. Yes? Okay, so let's summarize all this stuff. On the inside here, we have 4 different types of inequalities we can see. So I'm going to help you. This chart right here, if you look back at your notes for one thing, honestly, this chart's going to be very, very helpful. Okay? If we have gotten to the isolate step and your inequality looks like this. First of all, what symbol is that? What is that one called? Just greater than. Very good. So if we have greater than, or if we have greater than or equal to, because those are both greater at some point, this is going to be an or statement. We're going to be coloring on the outside. It's an or statement. We're going to be coloring on the outside. Okay, it's also called a union. You might hear some books and or people on the internet, if you Google around for help on this, calling that a union. That's okay. It's called a union. Now we would separate them into, again, exactly what we started with and then both flipping. Exactly what we started with and both flipping. And when we get to the graph, we're going to be coloring on the outside of the numbers. So let's say I have the solutions here and here. I don't care what these numbers are. We're just giving an example. For just greater, I would have an open circle on those numbers, and I would color on the outside of them. So going towards the 2 different arrows. So greater, open circle, outside. But if I had greater than or equal to, how would that change what my final graph looks like? Say again? No, well, it's still greater. What has changed? The closed circle, that's it, because now it's equal to. So it's the same or statement, still coloring on the outside, but since the number can be equal to that, I'm going to color in those dots so that they're filled all the way in. Do we see the difference between those two types of final answers? No line underneath it, line underneath it. Yes? Okay, on the other hand, if you have these two symbols, these are both the less thans. The less thans are my and statements. That's when we're going to color on the inside or between them because they're and statements. When you separate them, you would separate them into exactly what you see and then flip both the inequality and the sign. Exactly what you see and flip both the inequality and the sign. That's super important there that you remember to flip both the sign and the symbol. Okay, but this time when I graph it, let's say I have these two solutions. For the symbol less than, is that going to be an open circle or a closed circle? Open circle. And since it's an and statement now for less than, it's going to be colored in inside. Very good. My final answer for less than equal to, how does that change at all?
Closed circle.
Closed circle, but it's still filled in on the inside because it's still a less than symbol. So this is what our final answers will look like. I will ask for you to write the statements and either put the word and or in there, and then also give me a graph. Now, I didn't put number line graphs on all of our examples for today because we can draw a number line, okay? We can all do that. So we're going to be adding in our own number lines. Other than the change of flipping the symbol and the graphs being colored in, every other step is the same from when we did equations. Can we do an example together?
Oh, yes.
Okay, fabulous. In number 1, it says absolute value of x plus 7 less than or equal to 2. So first things first, what kind of statement am I going to have at the end? Is it going to be an and or an or statement? An and statement because it's less than, so that's an and statement. Just keep that in mind for the very end. We're still going to follow the old ISS rules. First ISS rule says to isolate the absolute value bars. Are the absolute value bars isolated?
Yes.
Cool, I'm done with step 1. This first S says to separate. I'm going to separate it into x plus 7, no more bars, and less than or equal to 2. No changes. No changes. And the second equation is going to be x plus 7, and then 2 changes. Flip the symbol, change the sign of C. Before today, when we did the separate step, all we did was do positive, negative. We're still doing that. We're just also flipping the sign. Okay, let's solve for x. How do we get this plus 7 to go away? Minus 7, and I'm going to do that on both sides. So this is the solve step. Should cross out my S, okay. And when we do this, the 7's cancel out. That's exactly what I wanted. I have x less than or equal to negative 5 because 2 minus 7 is negative 5. There's one of my inequalities. I just need the other one. But the steps are exactly the same. We're still going to subtract 7 from both sides. Get that 7 to go away. This would end up being x greater than or equal to negative 9. Bless you. Now, before I put my box, or I guess I could put my box already on top of these, but I have to put a word in between them. What word am I putting in between them? And. This is an and statement. So when I go to do my number line, I also know how I'm going to color this in. Now, I do not care how many numbers you put on your number line as long as these two critical numbers are on there and in the correct order. Negative 9 is less than negative 5, so make sure like you don't have them backwards because it's not how, bless you, how number lines work. Now, for this graph, am I going to put open circles or closed circles on those numbers? Closed, very good, because it's equal to, and I'm going to be coloring inside or outside? Inside. So all of the numbers in this domain from negative 9 to negative 5, so like negative 7's in here, right? Negative 7 would work. Negative 6 would work. All of those are solutions, but the moment I have a number outside of this interval, it's out. So that's the isolate, separate, solve. We're going to pause here and ask some questions. The question here was, how do we know if it's and or? You go to the isolate step, and once you're there, you look at this symbol. And this symbol that we had here is the symbol less than or equal to 2. You look at the isolate step. What is the symbol there? And you're like, all right, well, this is less than. And remember, less than, if you misspell it, is less than. It's an and statement. So we got to wait till we do the isolate step before we choose. That was a great question. Are there any other questions we can do? Can we do another example?
Yes.
Fabulous. Let's go to number 2. This time, we have absolute value of 2w minus 1 less than 11. So I'm going to start off with my ISS steps. Is this graph isolated? Yes, the absolute value bars are all the way by themselves on their side. So I can look at this symbol. What is the name of that symbol? Less than, which means, is this an and or an or statement? And. Okay, great. That means at the end, we're going to put the word and in between our final things. Fabulous. It is isolated. We know what's happening for the end. We separate. We separate it into 2w minus 1 less than 11, like literally exactly what it was without the bars, and 2w minus 1 greater than negative 11. Flip the symbol, change the sign. Then it's just solving steps. A bunch of inverse operations. We take care of getting rid of this first. That's the negative 1. How do I get rid of minus 1? Plus 1. And what I do on one side, I got to do on the other. Plus 1, plus 1. That'll go away. We're going to have 2w less than 12. What's the last step here? By. Very good, because I want that w all the way by itself. This would end up being w less than 6. Fabulous. I've got one of the 2 inequalities I need for my final answer here. But the steps to repeat the other one are the exact same. I'm going to let you guys do this one, because I just realized I haven't taken roll. If y'all will finish this one for me, let me take roll. All right, so if we would repeat these steps, this would be plus 1 on both sides. This time I'd end up with 2w greater than negative 10. Still divide by 2. Nice. Negative 10 divided by 2 is negative 5. Now, what's the word you should have put in between these two things? And. There we go. That's how we would answer this, specifically with the word and in the middle. If we were to graph this, I only really need to put those 2 critical numbers on here, but I make sure I put them in number order. Negatives go before positives, so I can put negative 5 first. Am I going to put open circles or closed circles?
Open and closed.
Ooh, they'll both be the same for this sort of thing. See how both symbols don't have the equal to underneath them? So they'll both be open. But we do the and stuff, bless you, which is in between. So no equal to underneath here means it's an open circle on your number line. How'd we do? What are we thinking? We're good? Okay, let's try another one. Thank you. All right, here we go. Number 3. Number 3, is it isolated?
No.
It is not, yeah. That absolute value bar is not the only thing on that side of the inequality. So we have to do something to get it isolated. How do we get rid of that big minus 4? Plus 4 on both sides. Fabulous. Okay, great. That's going to go away. We have absolute value of w divided by 3 greater than or equal to 2, because negative 2 plus 4 is 2. We check again. Is it now isolated? Yes. Okay, great. Now we can think about some things for the future of this problem. What kind of symbol is this?
Greater than, yeah, greater than or equal to.
Greater than or equal to. Fabulous. Is that going to be an and or an or statement? Or. Very good, because greater, if you misspell it or mispronounce it, is an or statement. We've isolated it. Now we just need to separate and solve it. Bless you. So separate, we have w divided by 3 greater than or equal to 2. Literally changed nothing besides the bars going away. And then we have w divided by 2. Flip the symbol, flip the sign.
What about 2?
Oh, you're right. That should be a whole 3. Hee hee. It's Monday. Okay. Now everybody's probably sitting here panicking because we're like, ooh, fractions, yuck. No big deal. Fractions are just division. So what's the opposite of division?
Multiply.
So when I start to try to solve this, what number am I going to multiply to make that divide by 3 go away?
3.
I'm going to multiply by 3. And what I do on one side, I have to do on the other. Those 3's cancel. This is just going to be w greater than or equal to 6. Same thing, if I am already dividing by 3, because fractions are division, all I have to do to undo division is to multiply. So again, multiply by 3. This is going to be w less than or equal to negative 6. Now before I put a box around these answers, what word do I put in between them? Or. If it doesn't have a word in between them, it is incorrect. I need to know if it's and or if it's or. That's super important for me. But we can also graph this. The two critical numbers that need to be on this number line are negative 6 and 6. Opened or closed circles? Closed. Very good, because they both have the line underneath the inequality sign. And since this is or, am I going to color it in between those 2 points? On the outsides. Okay. Those are all of the numbers for this union of graphs that I could use. Anything in the colored in point is considered a solution. Questions about this one? It's just the same like we've been doing, right? Just adding the little bit extra of and or statements. Fabulous. Oh, I didn't cross off these things. Okay. Number 4, on we go. Are the absolute value bars in number 4 isolated? No, super no, right? There's like a bunch of things happening on the outside that we need to take care of. Start with getting rid of the adding or subtracting always first. So how do I get rid of plus 1? Minus 1. Minus 1. Fabulous. This would end up being 4 absolute value 2x minus 5 greater than 20. What do I do to get rid of that 4? Because as of right now, divide it. Very good. I still want these bars all the way by themselves, so I'm going to divide the whole thing by 4 so that these 4's go away.
Yeah, 5.
Great. So I'm going to have absolute value 2x minus 5 greater than 5. Awesome. We're still just in the isolate step, no big deal, but now is the absolute value bars isolated? Yeah. So if I were doing my ISS steps, at this point, I could actually stop and think about what kind of statement I'm going to have at the very end. Because this symbol is greater than what kind of statement? And or? If you mispronounce or misspell greater, it's an or statement. So this is going to be an or at the very end. Great, now we know what to do. We just separate and we solve. 2x minus 5 greater than 5, and 2x minus 5, flip the sign, flip the sign. Can I leave you guys here to finish this one for me? Yes, I can. You got it. We've got through the isolate, separate step. We just need you to solve and graph it. You got it. Now that we've done this, we've only added the graphing and the addition of the and or statement into our problems. I do want you on the side of these notes somewhere to make a note for yourself. We didn't see an example of this, but it's really important that you remember what happens when you divide an inequality by a negative. Does anyone remember what happens? So if you divide by a negative number, okay, like perhaps you had negative 3x less than 9. What number would I have to divide by to get that x by itself? I'd have to divide by negative 3. When you divide by negative numbers, your spidey senses need to start tingling because we have to flip the inequality sign over when we divide by negative numbers. So if ever in the isolate step or in the solve step, you divide by a negative number, which might happen, you're going to have to flip that symbol. That's a rule for inequalities that we didn't see an example of. You might come across it on your homework. For the future, in case you need that, that might be really helpful. Okay, We got just a little bit more before we're going to get to independent practice time. We have a couple special cases. What do you notice about both of these special cases, number 5 and number 6?
Negative.
Oh my goodness, where's the negative? At the end. Last time, when we had isolated and equal to a negative number, was that ever allowed? No, so we need to know that these are special cases. These don't necessarily have no solution because we have to think for a second. This symbol says less than. Can absolute value ever be less than a negative number? Think about it. Can absolute value, which always has to be positive, can it be smaller than a negative number? No, there's no way it can be less than a negative number. So if you have a less than symbol, you're going to be able to say no solution, full stop, done. Because absolute value can never be negative. So it can't be smaller than a negative number. That would mean it's negative. But on number 6, what symbol is this? Oops. Greater than. Isn't absolute value, since it's always positive numbers are always greater than negative numbers, right? When you have a greater than symbol with a negative C value, you're actually going to say all real numbers. Because at all times, absolute values are going to be bigger than negative numbers. So in our special cases for inequalities, when it was a negative and it was equal to, we were like, no solution, done. For inequalities, we have to pause for a second and think. It cannot be less than, but it is always greater than. I missed it. Greater than. So there's 2 different answers for when there's negatives on the isolate step. So in the little box here, absolute value will never be less than a negative number. That's also less than equal to. But absolute value will always be greater than a negative number. So if you have a less than symbol, that's when you say no solution, NS for no solution. And when you have the greater than symbol, that's when you say all real numbers. So you can give me the fun and funky looking R, this one, the letters ARN, or the entire phrase, all real numbers. I accept any of those. There's infinitely many solutions to this because all of them will work. Okay, so here's where it comes in handy, as this is just a real world example of something that could possibly require you to think in absolute values. Not that you ever, when you're put in a situation, are going to get a piece of paper out and you're going to write down an inequality statement, but you need to be able to think through these things for yourself. Okay? You are buying a new computer. The table shows the prices of computers in a store advertisement. You are willing to pay the mean price with an absolute deviation of at most $100. You want to know what a good price of a computer is? And you either want to pay $100 less because you don't want a crappy computer, or $100 more because you don't want a more expensive computer. But you know the average price of a computer is this much. You don't want to get scammed, okay? You know that it'll vary a little bit. You're going to let yourself vary by $100. Okay, we need to know how many of these computer prices at the store are in our condition that we're going to be okay paying. It says that we are willing to pay the mean price. Does anyone remember what a mean means in math? It starts with an A. Average, absolutely. Mean price means the average price. So we need to find the average price of these computers. How do you find the average?
Add up everything and divide by 2.
Absolutely. So that's what we're going to do. You have a calculator to do it, but we're going to do 370 plus 890 plus 660 plus 725 plus 825 plus 670 plus 650 plus 450 plus 750, oh geez, plus 650. And how many are we going to divide by? How many computer prices is that? 10. Okay, in your calculator, please find me the mean price of these computers, or the average price of the computers on sale at the store. Okay, do y'all have my mean? What is the mean price here?
654.
664, yes. So that's the average price of a computer. And we're okay paying $100 more than that or $100 less than that. A deviation of $100. Specifically, at most $100. Those are the words we need to see. Well, when we were writing absolute value equations before, we had this formula that we're still going to use. The formula said absolute value of x minus the average or the midpoint, also known as the mean, equal to what's called the deviation or the distance. Well, we have both the midpoint, because that's the mean, and we have the deviation of $100. So let's write this inequality statement. We would say absolute value of x minus 664 and then something to do with $100. I need you to think back to Algebra 1. You learned this word right here, at most, that translates to an inequality sign. Think about at most. Can you spend more than $100 if you want to spend at most $100? No. Can you spend less than $100? Can you spend exactly $100? Yes. So when you say yes, you're saying that this symbol in between here is going to be less than and exactly equal to $100. Not more than, because it's at most $100. So you can go less than or equal to. This right here is the inequality that you would have solved in your head if you were actually standing in a store trying to decide if this computer is worth it. No, you're not going to get a piece of paper out and write this equation down and do all the algebra, but you're doing this algebra in your head as a consumer, as a person who shops. That's something that we do. But we're going to do it like it's a math problem because we're in math class. So what we would do after this, since it's isolated, we would separate x minus 664 less than or equal to $100. X minus 664, flip the sign, just like we did before. In both of these tiny little inequalities, how do we solve for x? How do I get rid of that? Plus 664, fabulous. When I plus 664 on both sides, I'm going to get x less than or equal to 764. And on the other side, x greater than or equal to 564. Ooh, you know what I forgot to do? I forgot to think about the word that goes in between this. It's an and, very good, because I used less than when I started this. This is going to be an and statement. Those are the inequalities that, again, I wouldn't compute on a piece of paper if I was standing in a store, but I would need to know that that's the most and the least that I'm willing to spend on this computer. My number line for this graph would look like this. 564 here, 764 there. I've got closed dots on both of those because it has a line underneath it, and I'd be coloring inside. Any computer on sale at the store that is in the colored in part of my number line is an acceptable computer for me to buy. It's not going to be too cheap and terrible, and it's not going to be too expensive. That's the budget I put for myself. So question, should I buy the computer price $370? No, cross that one out. We don't want that one. How about the $890? No. How about $660? Yeah. That one's okay. How about the $725? Maybe. How about $825? No. Do y'all know why they're saying yes and no? These numbers are either outside of the range, so we say no, or they're in this little section of colored in. Yeah. 670, is that in the colored in part or the blank part? Colored. So that one's allowed to be there. That's a good computer for me to look at. How about 650? Maybe. How about 450? No, outside of the range. How about 750? Maybe. How about 650? Maybe. So the question here asked, if we look back at what the actual question says, it said, how many of the computer prices fit your condition? So how many are left? 6. There are 6 that met our condition, so we could have up to 6 options fit our condition. We have 6 computers to really be looking at. The rest of them are either too cheap or too expensive. Again, this is something you would maybe do as a consumer, but you wouldn't sit down and do the math like this. This is why the math works, which is why you learn it like this. But you will be doing this kind of math in the real world, just not with like boop, 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 writing stuff down. You got to know if you're getting like ripped off at the store, basically.